Okay, welcome to another astronomy OpenStack short. We'll be looking at chapter 17, analyzing starlight. And so we'll start off by looking at the brightness of stars. And so stars' brightness for our purposes here on Earth, we're going to really talk about the parent brightness. Because if two stars are the same brightness, but one is further back than the other, one will appear brighter than the other. So the apparent brightness ends up being of most importance to us. And so we'll begin with luminosity. And so luminosity is the amount of energy radiated per watt. And what we see is that the luminosity is actually determined on the distance. So the further away you are, the less luminous something is going to look, because that same amount of light is spread out to through a larger area. And in fact, the luminosity is a ratio of the distance squared. So the brightness is going to depend highly on the distance. That's going to be one of the most important factors. So luminosity, as we said, is the amount of energy measured here in watts. And the apparent brightness is going to be that amount that reaches the Earth. We have a magnitude scale. It's a logarithmic scale. And the lower the number, the brighter the object. The sun is at the top of the scale at negative 27. We see the full moon. Venus is at about a negative 4. And the faintest object you could see with your bare eye would be at about a 6 on this scale. Anything higher than that will require a telescope or instruments to be able to view. And the Hubble Space Telescope could view objects as faint as about 30. Here are the logarithmic scale formulas, but really what's important to us is the difference here of apparent magnitude and absolute magnitude. So absolute magnitude is how bright a star actually is. The apparent magnitude is how bright that star appears to us from Earth. And so when we look at the wavelengths, we see that there's going to be colors associated with these stars. Hotter objects are going to emit at these higher frequencies because those photons are going to have higher energy. So we see hotter objects will be more bluish in color. Cooler objects will be more reddish in color. And when we look at the spectrums, we see that the hottest stars are at about 50,000 degrees Kelvin, and the coolest stars are at about 3,000 degrees Kelvin. Our sun, just as a reference, is at about 5,800 degrees Kelvin. And so here in this image, every single dot represents a star, and we could see some coloration. Reddish on the cooler end, some yellow, a little bit warmer, and then some bluish and white stars, which will represent the hottest stars. So when we look at the spectrum here, we classify certain stars. Our spectrotypes are O, B, A, F, G, K, M. So O being on the hottest, and then M on the coolest. And so, for example, if we look at B-type star, the surface temperature could range anywhere from about 10,000 to about 33,000 degrees Kelvin. That's where we see those spectral lines or those absorption lines there peak. when we look at those absorption lines, we could see the specific elements there of where they actually peak, and so that corresponds to an approximate temperature. So within our classification of the stars with temperature here, the OBAFGKM, one way to remember that is OBA, fine girl or guy, kiss me. That's in many astronomy textbooks. And so within each of those categories, it breaks down into a subdivision of 10. So, for example, G-type stars will range all the way from 0 to 9. So 6,000 being on the hotter end down to 52 on the cooler end. The Sun is a G2 star, which puts it at about 5,800 degrees Kelvin. So when we classify stars on the spectral type, they'll have one of these letters associated with them along with an additional number. So a sub category within that temperature rank. And so much credit goes to Annie Jump Cannon and really a whole group of researchers at Harvard who laid the foundation for classification. Unfortunately, late 1800s, early 1900s, women professors were not given their fellowship at most universities. And so a lot of them had to work under male instructors and did not get the proper credit. So Annie Jump Cannon now gets credit for being a professor and who really laid the foundation during that time. And so her work gets extended now. We have now noticed that this ranking actually extends down. We have L, T, and Y class stars as well. And we see that there's a lot of brown dwarfs that were found within this category here. And so brown dwarfs are really what we consider failed stars. They have less than 0.08 solar mass. And so if you have more than 0.08 solar mass, that'll be enough material for nuclear fusion to occur, and a star could actually spark and become alive. If you don't have that much mass, you're going to be a failed star. So we call those brown dwarfs. And they're held together by degeneracy pressure. So unlike a star that fuses and it has a gas pressure pushing back out against gravity, degeneracy pressure pushes back because there's only a certain amount of space that you could compress atoms into. So much like trying to shove a lot of clothes into a suitcase, at some point that is going to push back at you. So degeneracy pressure stabilizes it, pushing against gravity, and the temperatures are extremely cool here. This is an image looking at Orion, and each circle here represents a brown dwarf, and we're looking at it again, detecting it not with visual light, but detecting the warmth there in different parts of the electromagnetic spectrum. I believe infrared. And so we could also use the spectrum here to measure some different characteristics of the star, specifically its motion, moving away towards us, and rotation as well. So if you recall, if we look at the spectrum of a star, we could identify it with a red and blue shift, that Doppler shift. So objects moving away will have their spectrum lines move towards the red end, and those that are moving towards us will go towards the blue end. And so we could use that to measure stars and their velocities. So one thing to note though is if a star is moving kind of parallel with us, we're not going to really notice that that velocity or that change. So that's our transverse velocity. If it's moving directly away from us, the radial velocity, we'll be able to detect that whole entire motion. Now, most stars aren't going to move exactly parallel or perpendicular to us. They're going to have kind of at an angle, which we call the space velocity. So we won't be able to detect all of the radial velocity, but we'll be able to put a limit on that, and we'll be able to detect some of that motion. We could also use that for rotation. So using the spectrum, if we look specifically at a star, we could see that those absorption lines shift ever so slightly into the red and blue. So when the star is rotating towards us and then away. So with that, we're able to get some estimates. So for example, the sun rotates, roughly 24 to 30 days. Altair would probably be somewhere in the neighborhood of about 6.5 hours. So the spectrum allows us to have classification for stars with temperatures, and it also gives us information on the motion, so how they're moving away from us and their rotation as well.